We used modern AI simulation to visualize the invisible forces that caused the Hyatt Regency walkway collapse. On July 17th, 1981, the atrium of the Hyatt Regency in Kansas City was hosting a tea dance. Above the lobby floor, two suspended walkways, elegant steel and concrete structures, spanned the open space at the second and fourth floors. The design was striking, ambitious, a testament to modern engineering. But hidden within those elegant lines was a flaw, not in the grand vision, but in a single, seemingly minor fabrication change, a change that no one caught, a change that transformed an acceptable design into a structure that was holding twice the load it was engineered for. This is the story of how a modification during construction, intended to make fabrication easier, became one of the most studied structural failures in engineering history. Let's analyze what happened. To understand this failure, we need to understand what the walkways were supposed to look like and what they actually became. The original design called for three suspended walkways in the atrium, one at the second floor, one at the third, and one at the fourth. But during construction, the third floor walkway was eliminated. That left us with two walkways, one directly above the other. Here's the original concept. A single, continuous steel rod, about 30 feet long, would hang from the ceiling structure. This rod would pass through the fourth floor walkway's box beam and continue downward through the second floor walkway's box beam, ending with a nut at the bottom. Think of it like threading two picture frames onto one long piece of wire. The weight of both walkways would be supported by the ceiling connection. Simple, clean. From a structural standpoint, this is elegant. The ceiling connection carries the entire load. Each walkway hangs independently on the same rod. The fourth floor connection? It only has to support its own walkway. From a structural standpoint, this is elegant. But there was a practical problem. The steel fabricator looked at this design and realized, threading a single 30-foot rod through both box beams, especially with the tolerances required, was going to be difficult. Time-consuming, expensive. So they proposed a change. Instead of one continuous rod, they'd use two separate rods. The upper rod would hang from the ceiling and connect to the fourth floor walkway. The lower rod would hang from the fourth floor walkway and connect to the second floor walkway. To the casual observer, this looks almost identical. The walkways are still suspended. The rods are still there. What could be the difference? Everything, and this is where the physics becomes critical. Let me give you an analogy. Imagine two people hanging from a tree branch by a rope. In the original design, they're both holding the same continuous rope. The branch supports both of their weights. The upper person's grip on the rope? They're only supporting themselves. Now imagine the modified design. The upper person holds a rope tied to the branch, but the lower person isn't holding that same rope. They're holding a different rope, tied around the upper person's waist. Suddenly, the upper person's waist isn't just supporting them, it's supporting both people. The load on that connection point has doubled, and that's exactly what happened at the Hyatt Regency. Here's the engineering reality. In the original design, the fourth floor box beam connection carries only the weight of the fourth floor walkway, about 31,000 pounds. The load from the second floor travels straight up through the continuous rod to the ceiling. In the as-built design, that fourth floor connection now carries the weight of both walkways, roughly 62,000 pounds, double the load. Building codes require a factor of safety. Structures must be able to carry more than their expected load. The original design had that margin. The modified design? It eliminated that margin entirely. Under normal conditions, the walkway carrying just its own weight, this connection was already stressed near its limit. Now add people. Modern computational tools allow us to visualize what happened at the structural level. Using physics-based simulation, we can recreate the stress conditions that existed in that connection on July 17, 1981. Let's start with the walkway under normal occupancy. People are standing, walking, gathered in groups. Watch the stress distribution. The box beam is doing its job, distributing the load along its length. But look at the connection point where the rod meets the box beam. It's already showing elevated stress. Yellow, orange. The load is concentrated on that small washer plate. The nut presses upward against it. The steel begins to yield, to deform permanently. This is happening on a scale of fractions of an inch. invisible to anyone in the atrium. But at the molecular level, the crystalline structure of the steel is rearranging, slipping. On that evening, approximately 1,600 people were in the atrium. Many were on or near the walkways. The fourth floor walkway was packed. The stress at that connection is now critical. The washer plate is bending. The thin walls of the box beam are flexing outward. The nut is beginning to punch through. The failure, when it begins, happens faster than human perception. The nut punches through the washer. The rod pulls free. The fourth floor walkway begins to fall. Without the support of the upper rod, the fourth floor walkway falls approximately 12 feet directly onto the second floor walkway below. The second floor walkway, never designed for this impact load, fails immediately. Both structures fall to the lobby floor. 114 people lost their lives. More than 200 were injured. It remains one of the deadliest structural failures in American history. The investigation that followed was exhaustive. The National Bureau of Standards, now NIST, conducted a detailed forensic analysis. What they found was clear. The connection failed because it was carrying twice the load it was designed for. But the question became, how did this change get approved? The fabricator's modification was never checked by the original structural engineer. The detailed drawings were stamped and submitted, but the calculation verifying the load capacity of this new connection? It was never performed. In the investigation testimony, it became clear that there had been a breakdown in communication. The fabricator believed the engineer had approved it. The engineer stated they never performed a detailed review of the changed connection. This wasn't about anyone's competence. These were qualified professionals. This was about a system that lacked sufficient checks. Engineering failures are rarely caused by one mistake. They're caused by multiple safeguards failing simultaneously. The design was changed. The change wasn't properly reviewed. The calculations weren't redone. The inspections focused on workmanship, not design verification. Every checkpoint was passed without the error being caught. The consequences were severe. The engineers involved had their professional licenses revoked. The engineering firm closed. Legal settlements totaled hundreds of millions of dollars. But more importantly, this failure changed the profession. The lessons are straightforward. Every modification must be reviewed as thoroughly as the original design. Load paths must be explicitly verified, not assumed. Changes require calculations, not intuition. And communication between designer and fabricator must be explicit and documented. Thanks for watching. If you found this analysis valuable, consider subscribing. We explore the engineering lessons behind major structural events, always with respect for their human impact. Until next time, check your assumptions.